Solving systems of linear equations, the elimination method. So let's talk about the goal for this method. The goal for the elimination, sometimes called the addition method, is that we need the coefficients of the same variable to be opposites. We need the coefficients of the same variable to be opposites. So here I have two linear equations. I have a system of linear equations, 7x plus 4y equals 2 and 9x minus 4y equals 30. So the other thing that's important is that we need to have all the variable terms on one side and then all the constants on the other side. And then what we need is a situation like what's happening right here, which is that the variable y has a coefficient of positive 4 in the first equation and negative 4 in the second equation. So I have a pair of variables that have opposite coefficients. So that's the goal. That's what I need to happen. And in this one, it's already happening, but it's not always like that. So to obtain that scenario, we can multiply one or both equations by non-zero numbers to get opposites in front of the same variable. So that's what our goal is going to be, to use this elimination or addition method. Let's take a look at an example. We want to solve by the addition or elimination method here. So let's go and take a look at the steps here. So rewrite both equations in the form ax plus by equals c. If I take a look at my system, I have 3x plus y equals 10 and x minus 2y equals 5. So I do have the variable terms on the left and the constant terms on the right-hand side, so on separate sides of the equation. So now I want to multiply either one or both equations by non-zero numbers to get, again, those opposite coefficients in front of the same variable. So let's come back over here and focus on one variable at a time for a second to just think about this strategy. So I'm going to focus on the x variable right now. So if I look at the x variable in the top equation, I have a coefficient of 3 in front. On the bottom equation, I have a coefficient of 1 in front. So if I wanted to make these opposite coefficients, I would strive to turn the 1 into a negative 3 by multiplying the entire bottom equation by negative 3. Because in an equation, whatever I do to one side, I have to do to the other side to balance it out. So that would be a really easy way to get these to be opposite coefficients. So I'm going to keep the top equation the same. So what I'm going to do is just recopy it over here. So I have 3x plus y is equal to 10. And in the bottom equation, I'm going to multiply it by negative 3. And I like to indicate what I'm doing on top of my arrow here. So I have to multiply 1x times negative 3, and that's going to give me negative 3x. I have to multiply negative 2y times negative 3. That's going to give me a positive 6y. And I have to multiply 5 by negative 3. So that's going to give me negative 15. So every single term gets multiplied by negative 3. And what I've done is I've created my terms with opposite coefficients. So I have positive 3x and negative 3x. Now the reason this is often called the addition method as well as the elimination method is because that's the next step. Step 3 is add the two new equations to eliminate one of the variables and solve for the remaining variable. So what I'm going to do here is I'm going to think about adding down, in other words. So 3x minus 3x will cancel on purpose. We designed that to happen so that all we have left is y plus 6y, or 7y, is equal to, and then here I have 10 plus negative 15, so I have negative 5. So now I can solve for y by dividing both sides by 7. So I end up with y equals negative 5 over 7. And then that's half of the answer. Remember, our answers to a system of equation is a coordinate point in x comma y. So now we take the y value and we can plug it into any equation that has both an x and a y in it. So I'm going to go ahead and take this bottom equation here. So I'm going to take x minus 2y is equal to 5, and I'm going to plug in negative 5/7 for y. So I have x minus 2 times negative 5/7 is equal to 5, or x plus 10 over 7. So I multiplied negative 2 times negative 5 and 1 times 7, and then is equal to 5. And then I'm going to go ahead and subtract 10 over 7. So I have x equals 5 minus, so 5 over 1 minus 10 over 7. And then here, to remember to subtract fractions, we need it to have the same denominator, so we'll multiply the top and bottom by 7. So we have 35 over 7 minus 10 over 7, which is 25 over 7. So this is my value for x, my simplified value for x, and this is my simplified value for y, so we write our answer as a coordinate point, 25 over 7, negative 5 over 7. So this is my answer. So we wanted to write your answer in the form of x comma y. So the note here says that if you're doing this process and all of the variables cancel out, but you end up with a true statement, the answer is going to be infinitely many solutions. And if all the variables cancel and you get a false statement, then the answer is no solution. Let's go ahead and solve again by the addition or elimination method. In this example, I have 3x plus 4y equals negative 10. The bottom equation is 5x equals 3y minus 7. So I'm going to have to start by subtracting the 3y to the left side to get my variable terms on the left. So I'll rewrite the top equation. That one is fine. The bottom equation will become 5x minus 3y is equal to negative 7. So I keep the negative 7 on the right. Now if I go ahead and look at the coefficients of the same variable, so I have a 3 and a 5. So that's not going to be as easy as the last one to make them opposite coefficients because I don't have a 1 in front of one of the variables. So the x variable isn't going to work for us quite as easily. We'll go ahead and check the y variable. So the y variable has a positive 4 and a negative 3. So they're opposite in sign, but they don't have the same number. So I don't have opposite coefficients, just opposite signs. So I'm going to go ahead and make the y variable have opposite coefficients. And the coefficient that I'm going to make them have is the least common multiple. So between 4 and 3, the least common multiple is 12. So that's the smallest number that we can evenly divide 4 and 3 into. So in order to turn this 4 into a 12, I have to multiply it by a 3. So I'm going to take the top equation and multiply by 3. So it's going to become 9x plus 12y is equal to negative 30. So remember, each term gets multiplied by positive 3. So now the y variable has a 12y in front. Now I want the second equation to have a negative 12 in front. So I'm going to have to multiply the bottom equation by a positive 4. So the first term will be 20x. The second term, by design, will be a negative 12y. So that I do have opposites in front of the variable y, positive 12 and negative 12. And then I'm going to have negative 28. So we have 4 times negative 7. So we do need those opposite in sign but same number coefficients so that when we add in the next step, we end up with 29x. So the x variable stays this time because we're eliminating the y variable. And then we have equals negative 58. And then we divide both sides by 29, and this actually divides in evenly so that we get x equals negative 2. And once we get one value solved for, we take that value, and just like the substitution method, we can plug it into any equation that has x's and y's. So either of these originals, we could, if we wanted to, even plug it into either of these equations that have both an x and a y involved. So I'm going to go ahead and plug it into this top equation here. So I have 3x plus 4y is equal to negative 10. So I'm going to plug in the negative 2 for x, plus 4y equals negative 10. So negative 6 plus 4y equals negative 10. If I add the 6 to the other side, I'm going to end up with a negative 4. So adding the 6 over gives me a negative 4. Divide by 4, and I get y equals negative 1. And then remember that we write our answer as a coordinate point, so negative 2 first, the x value, followed by the y value, positive 1. Alright, let's look at this next example. We have 2x plus 8y equals 6, and we have 15 minus 20y equals 5x. So in this top equation, 2x plus 8y equals 6, I do already have the variable terms on one side and the constant on the other side. But one of the things I want us to recognize is this is fine, we can leave it like this, but all of the coefficients are divisible by 2. So what I can do is I can divide each term by 2, because it's like multiplying each term by a half, just to make the coefficients a little bit smaller and nicer to work with. So although I could keep the equation exactly the same, the other thing I could do just immediately is divide everything by 2, so that I'd have x plus 4y is equal to 3. And now I have a 1 in front of the x, so that's nice for the elimination method. So we're going to leave that equation here. Now on this equation, I have 15 minus 20y equals 5x. And maybe the first thing we want to try to do is get all the variable terms on one side and the constant on the other side. So I'm going to subtract the 5x to the left and subtract the 15 to the right. So I'm going to have negative 5x and then minus 20y is equal to negative 15. So now I can do one of two things here. So I can recognize, just like in this last example, that each of these coefficients is divisible by 5, and they also all have a negative in common. So I can divide each term by a negative 5. Or I can look at the fact that this top equation here, the variable x has a 1 in front, so I can multiply each term by a 5 so that I can end up with positive 5x and negative 5x. So it doesn't really matter which method we choose, just so that we're varying things a little bit. Let's divide each term by a negative 5 here. So the top equation is going to stay the same. X plus 4y is equal to 3. Here I'm going to divide everything by negative 5. So I'll get positive x, positive 4y, positive 3. And if we proceed with the elimination method here, then our goal would be to make the terms have opposite coefficients. So there's a positive 1x here and a positive 1x here. So let's go ahead and make either one of these negative 1. So let's go ahead and multiply, let's say, the top equation by a negative 1. So multiply the top by a negative 1 so that I have negative x minus 4y equals negative 3. So multiplying each term by a negative 1. And then the bottom equation stays the same. So I have x plus 4y is equal to 3. And so now when we attempt to add these two equations together, we end up with, well, negative x plus x. On purpose, we were aiming to make that a 0, so that term is gone. But negative 4y plus 4y, well, that's 0 too, so we have 0 plus 0 is equal to negative 3 plus 3 is 0. So we ended up with a true statement. And that's because, and I'm sure some of you caught it, that these are actually the same line. It was very visible right here at this step. X plus 4y equals 3, x plus 4y equals 3. Well, they're the same exact line. So they're going to meet everywhere. There's infinitely many solutions. But there's a particular way that we write this. So it's true that there are infinitely many solutions, but we actually have a more formal way to express all of those solutions. So what we do is we say, well, all coordinate points work. All x, y's work such that, and what we do is we take either equation, because they're the same equation, and we solve it for y. So all the coordinate points x, y work such that, so I'm going to have to do this scratch work on the side for a second. I'm going to take x plus 4y equals 3. So I'm going to subtract the x, so negative x plus 3, and we divide by 4 everywhere. So I have y equals negative 1/4 x plus 3/4. So we say that there's infinitely many solutions, and those solutions are all the points x comma y such that y equals negative 1/4 x plus 3/4. And we write that in these braces here. So it's true there's infinitely many solutions, but we know exactly what solutions those are. It's every single point on this line. It's every single point on this line. So this is that set builder notation that we learned back a while ago when we were looking at interval notation and set builder notation. So this is all coordinate points x, y that are on this line that satisfy both equations because they're the same equation. And in this next example, we'll solve again by addition or elimination. So here we don't have the variable terms on the same side. We'll have to subtract the 4x and subtract the 3x. So we end up with negative 4x plus 7y equals 8. And here we have negative 3x plus 4y is equal to 6. In this next example, we're going to again solve by the addition or elimination method. So let's go ahead and start by making sure the variable terms are all on one side and the numbers are on the other, the constants. So I'm going to subtract the 4x and add the 2x to the other side. So I'm going to end up with negative 4x plus 7y is equal to 8. The bottom equation, if I add the 2x, I get positive 2x plus 4y is equal to 6. Now on this one, if I look at the x variable, so I don't have opposite of the same coefficient. I have a negative 4x and I have a positive 2x. But 2 divides evenly into 4. So if I multiply the bottom equation by a positive 2, that will make this coefficient a positive 4, which is opposite of the negative 4. So that's going to be the easiest thing to do here, to use the elimination method, because if I look at the y variable, 7 and 4, they are not opposites already, and they're not multiples of one another, so 4 doesn't go into 7 or 7 doesn't go into 4, so I'd have to multiply both equations by a number. Instead of, if I choose the x variable, I can just multiply the bottom equation by a positive 2 and the top equation can stay the same. So the top equation will stay negative 4x plus 7y is equal to 8. The bottom equation I'm going to multiply by 2. So just a positive 2 because I want them to have opposite coefficients. So I'm going to have a positive 4x by design. If I multiply by 2 here, I get 8y. So plus 8y is equal to, if I multiply 2 times 6, I get 12. So now I can add the two equations together. So the negative 4x and the positive 4x will cancel. So it's important to make sure that they're not the same number, that they're opposites of one another. So negative 4 and positive 4. So it's probably the most common mistake is making them the exact same number. So thinking to multiply this by negative 2, but then they won't cancel out. So in this example, they do cancel out. So the x's are gone. I have 15y is equal to 20. And if I divide both sides by 15, then I have y is equal to, if I reduce this to lowest terms, they're both divisible by 5, I get 4 over 3. And then I can take y equals 4 over 3 and plug that into any equation that has an x and a y. So I'm going to go ahead and plug it into the top equation. So I have 7y is equal to 8 plus 4x. So 7 times 4/3 is equal to 8 plus 4x. So we're going to have to do a little bit of work here because we have, let's see, 28 over 3 is equal to 8 plus 4x. So if we subtract the 8, 28 over 3 minus 8 over 1 is equal to 4x. So we need common denominators here. That denominator will be 3. So I multiply the top and bottom by 3. So I'm going to bring my work up here. I have 28 over 3 minus 24 over 3 is equal to 4x. So we're at 4/3 is equal to 4x. So to solve for x, I would divide by 4, or the other way to think about this, because this is a fraction over here, so I don't really want to write it. I'll kind of do it at first, but then I'm going to erase it. I don't want to think about it as 4/3 divided by 4. So what I want to do instead is think about I'm multiplying by the reciprocal of 4. I'm multiplying both sides by 1/4. So the 4's will cancel, and I end up with a 1 over 3. Here the 4's cancel, is equal to x. So it's a nice little review of solving a linear equation with some fractions. But my final answer to my original question is the coordinate point 1/3, 4/3.